I guess the homework didn't post.
Yep. Blank page.
Huh?
It was a blank page.
Yeah, that is on, I'm not double checking. I'm gonna go through the shields business with you, and I want you to tell you that shields primarily are things that you want to make out of metal, and you want a minimal thickness of metal that gets the job done. That's the whole idea with shields. We're gonna go through the planar shield one more time, and shielding effectiveness, yes, go to the mic, yes. And then we'll do filters. If we have time to go through the actual standard clock cycle, clock waveform, and the actual frequency response, and how to analyze things. When we're talking about real EMC, almost all the EMC problems these days stem from clocks. All of your devices run on digital clocks that go from 0 to 5 volts or so. Well, that has a huge spectrum. The rise time and fall time tell you where the frequencies are, but when you analyze EMC interference, like on something like a laptop computer, it's primarily the clocks that are the problem. It's not the 120 hertz signal that it used to be that would come in through the transformer. It's really the clock, and I'll get to that if I can today. If I can't, then so be it. So this is going to be shields again. And we'll start with planar shields. When I talk about a shield in general, it's to prevent signal from passing from one domain to another. Normally you want to prevent things from getting into sensitive equipment, or if it's FCC regs, you're trying to prevent things from getting outside of a noisy environment that would violate the Federal Communications Commission standards. So we start with a planar shield, and in general, I did this last time, if the shield has a certain thickness, and I'm going to use the thickness as D. In the book, Wentworth uses T. I prefer D for a reason. All right. Now, with that, this shield is also going to have sigma of the shield inside. There may be a value of mu relative that is not 1. But primarily, epsilon and omega, usually for a shield, not always, but normally sigma of the shield is much, much greater than omega epsilon inside the shield. That's normally the case, which means this is a very good conductor. Think of it as copper or aluminum or steel. Steel in particular is unique because steel has a mu relative. 1045 steel has a mu relative of about 1,000, which gives you even more shielding effectiveness. Now, when you have a wave coming in, this is the standard wave, they assume it's normally incident. We don't do oblique incidence on shields because you always worry about the worst case, which would be normal. There's going to be a field that's actually incident on it. We know we get some of this reflected that way, and some of it passes. There's going to be a field in the shield itself, inside here, and this field is going to monotonically, or it's going to exponentially decay inside there, and then it's going to pop out the other side, and there's going to be the transmitted field. So finally on this side, there's a transmitted field. Oh, I'm sorry about that. Tell me when it's fine. Is that okay? All right. So here's what I generally do this as simple as possible. When I look right here at this boundary, there's going to be a transmission coefficient tau 1. All right, now I'll get to what tau 1 is in a second. There's going to be a transmission coefficient here, and that would be tau 2. And the thing that causes this to decay is going to be alpha. And here it's going to decay inside this region as e to the minus alpha d, really. Now I'm going to just try to talk you through all this to make sure everybody's clear about all these steps. These shield problems are very easy, but unfortunately it's very easy to mix something up. So the first thing you always do with a shielding problem is find out what the actual intrinsic impedance of the shield is. So for the shield, the standard form is j omega mu over sigma plus j omega epsilon. Now mu is mu naught times mu relative, so I'm going to put that in there because a lot of people forget there's a mu relative, and when it's steel, steel has a mu relative of about 1,000. It's not 1. Everybody understand that? Usually epsilon, normally this is not, this term right here is about 0, all right, compared to the value of sigma. Usually. Now, we do an approximation, and we say if sigma is much, much greater than omega epsilon, then this boils down to just the square root of j omega mu naught mu relative over sigma. And you can leave it like that. In truth, the square root of j is really e to the j 45 degrees, or j pi over 4. I'm going to make a comment about this because this is something that comes up over and over again. If you have the symbol j, technically j is the square root of -1. Actually, it's going to be plus the square root of -1. Square root of -1 is actually plus or minus j. But for now, we're going to just treat it as this. Now, the normal way to write this in complex domain is e to the j pi over 2. That's normally the way we write j. Y'all follow me in that class? That's just it. Now, if you take the square root of j, it's like taking the square root of e to the j pi over 2. Well, the square root is just, you're taking something to the 1/2 power. So that's the same thing as e to the j pi over 4. Does everybody agree with that? Make sure you see this. I know it's trivial once you see it, but some people don't see it. Now, e to the j pi over 4, mathematically, if we used Euler's identity, that would be the cosine of pi over 4 plus j times the sine of pi over 4. I do this in my EMC class because people miss subtleties here. Everybody agree with that? What is the cosine of pi over 4? 1 over square root of 2, right? What is the sine of pi over 4? 1 over square root of 2. So this is oftentimes rendered as just 1 over the square root of 2 times the quantity 1 plus j. Just keep that in mind. I'm showing you things that you'll come across over and over again. So the square root of j is 1 plus j over the square root of 2. That is a standard way of rendering it. Why is that important? Because here I can say that this is actually equal to simply e to the j pi over 4 times square root of omega mu naught mu relative over sigma. Or I can go a step further and say it's also equal to, if you want to, you can do it this way. If I put in 1 plus j over the square root of 2 in there, so I'm going to have 1 plus j over the square root of 2 times, and then the square root of omega mu naught mu relative over sigma. I'm going to put in 2 pi for omega. So it would be 2 pi f for omega, mu naught mu relative over sigma. And you can see right here, I can get rid of that root 2. I'm just showing you how it appears in a lot of places. They're all the same, but I'm going to make sure when you see this, you don't say, hey, that's not what we were taught. So you'll make sure you at least identify the similarities. This right here, 1 plus j times the square root of pi f mu naught mu relative over sigma is just another way of writing this. They're all the same. I mean, this has no assumptions. If this is true, then all these are true, and you're going to see all forms of that. I just want to make you aware of it, so you don't, if you see any of these forms, you're not shocked or think it's wrong. Okay, those are all the same things. You get eta shield first right here. Next, you're going to go ahead, it doesn't matter what form, almost always that's going to be the case. So you're going to get one of these forms for eta shield. Then you get the transmission coefficient of the first here. Now that's equal to 1 plus the reflection coefficient of the layer between eta naught and eta shield. They're the same. You add 1 plus reflection, you get transmission. The common way to write this is it's actually 2 times eta shield. It's twice the actual impedance you're going into divided by eta naught plus eta shield. That's normally the way it's written. Please watch this. This is important what I'm about to tell you. Now these are standard approximations that save you a lot of time. Then here, and write down, I'm going to put down if, and only if eta shield's magnitude is much less than eta naught. I know more than an order of magnitude. All right, if eta shield is, say, I don't know, 2.5 at an angle of 30 degrees and eta naught is 125, that's much, much less. If that's the case, then we can say that tau 1 here, the transmission coefficient, is approximately 2 times eta shield, all right, over eta naught, because this number compared to that number is insignificant, and that's normally done. That's tau 1. I went through this last time. I'm making sure everybody sees it. We'll do a problem too. The next thing you run into is this. We need tau 2. Well, tau 2 is going to be the transmission coefficient going from the shield out to free space again. And by the way, I know they're complicated problems you can create, but almost all shields have air on both sides. Almost all the shielding problems you run into assume air on one side, air on the other. Very rarely do you have to worry about something else. And we don't generally get into multi-layer shields. Even though that's addressed by some people, you don't need that level of complexity. You just, get the metal thick enough and it stops everything. That's the basic thing. Because that's what you're going to be doing, designing stuff, not analyzing it. In the real world, generally, most of your work is design. It's not analysis. Unless they've created something, there's a problem. Then you got to analyze what's wrong. So tau 2 is going to be twice the impedance you're going into. What's that impedance? If we're in the shield and we're going out of the shield, what's the impedance we're going into? Or, right, leave it as eta naught for now, right? Over eta naught plus eta shield, right? Now, look at that for 1 second, and you can see that if we make the assumption that eta shield is much less than eta naught, and you can put magnitude here, follow me? Then what happens to this number? You cover up the shield, you get 2, don't you? Sure, you get 2. So that means the magnitude of the transmitted field, and never worry about phase when you're dealing shielding effectiveness or shielding. They don't care about that. When I look at the actual transmitted field and the total transmitted field, I can say that E transmitted, and this is going to be the magnitude of the transmitted field, will be equal to E naught incident, just magnitude of that. Then it's going to be times tau 1. Well, tau 1, in this case, is going to be equal to, if we make those assumptions, tau 1 is 2 eta shield over eta naught. Right? And put a magnitude there, too. You care about the magnitude of tau. It will have an angle, but don't worry about it. It's always magnitude. Got me? Then it's going to be times e to the minus alpha d. And put a magnitude there. Now I got to talk about that. The alpha I'm talking about really comes from gamma inside the shield. If you're inside the shield here, please follow me. Inside the shield, the propagation constant is equal to the square root of j omega mu times sigma plus j omega epsilon. And that propagation constant is alpha plus j beta. Do you all agree with that? All right, now you have to know this. Follow me, everyone? Alpha plus j beta. All right, now we make the assumption, I'm going to work right there. If I assume that sigma is much greater than omega epsilon, that's almost always the case for any decent shield, or else you wouldn't be making it. You wouldn't use a material where this wasn't the case. It would be foolish if you're making a shield. Now, follow me on this. Do you all see how this cancels right here? If that's the case, right? And if that's the case, what happens? I'm going to go to this side, and I want to make sure you all see this. I come over here and I say, if that is the case, then this becomes equal to, matter of fact, let me write it up here because I'm going to say, therefore, gamma will be equal to the square root of just j omega, and then it's going to be mu naught, mu relative, times sigma. I want to make sure I've gotten rid of this j omega epsilon. Everybody see that? You got calculators. You can put it in if you want, but it's an insignificant thing. Doesn't matter. Well, if you look at this, now remember what I told you about the square root of j. That's actually equal to 1 plus j over the square root of 2. Correct, class? And I think, is that still up there? Right? So put it in. You put 1 plus j over the square root of 2. and then times this inside, which is omega mu naught mu relative sigma. Well, omega is 2 pi f. I'm doing this for a reason. This is the way it usually appears. So it's 2 pi f times mu naught times mu relative times sigma. Now, everybody see this? What do you notice here? You notice the square roots of 2 cancel, correct? So get rid of them. I'm going to get rid of this one right there and there. And now I have pi f mu sigma times 1 plus j. What it means is here is that alpha plus j beta imply that alpha is beta, if you can see this. J, the coefficient of j is beta, coefficient of 1 is alpha, right? And in both cases, they're equal to the square root of pi f mu sigma. I'm going to leave it as that. Well, what is the square root of pi f mu sigma? Exactly, and 1 over the skin depth becomes a critical thing when you talk about shields. It's what the skin depth is. So this is really simply 1 over the skin depth. Really, 1 over the skin depth. And that's the symbol for skin depth. So that means alpha here, I can put in as pi f mu sigma if I wanted to, and I will in a second, but this is the general form. Now, when we talk about shielding effectiveness, and almost everything that you're going to hear about shielding, and something we're going to talk about with filtering is going to be insertion loss and reflection loss, and all these things are in dB. Almost always in the real world, when you're dealing with stuff, I can't think of a case you don't, you talk about the dB of effectiveness. So the shielding effectiveness of a shield is defined as this. We could do it with power, but I prefer we do it with just electric field voltage per meter. It's 20 times the log, all right, of the magnitude of this. You take the actual incident electric field, that's with no effects of the shield, and divide it by the actual transmitted field through the shield. Now here's what this comes out to be. Remember, this is a magnitude. We care not about phase. That's the incident field, whatever it was. That's the field that gets through the shield. So this is a lot smaller than this, hopefully, right? Means this is going to have it's going to have a magnitude greater than 1, hopefully a whole lot greater than 1. And the log of that times 20 tells you the shielding effectiveness, how effective the shield is. So if you put in the numbers here, 20 times the log, right, of the magnitude, you can see right away that the E naught incident here will cancel this E naught incident. I could put a little naught there, right? And to the transmitted field. Those go away, so I'm left with 20 times the log of 1 over this. So it's going to be 2. That's going to be downstairs, and then it's eta shield, right, over eta naught. And then it's going to be, I got to actually multiply that by 2 again. That's actually going to be the transmission coefficient tau 1. Then it's times e to the minus alpha, and alpha is the square root. Or really, I'm just going to put this as simply d over the skin depth. So it's e to the minus d over the skin depth. And then it's going to be times 2 because, remember, the transmission coefficient right here is just 2 for a shield. This almost always is the way it is. And that's magnitude. Now, you can see here that this really breaks down to be simply 20 times the log, right, of the magnitude. And take a look at this. I can get eta naught over eta shield. Shield here, take 1 over this thing, right? It's divided by 4 because it's 2 times 2. And then it's times e to the really alpha, or d divided by the skin depth here. And that's the shielding effectiveness. I want to tell you something about this. Oftentimes they break out how much shielding is caused by the actual attenuation. So what they'll do is take this and they'll break it into parts. They'll say this is 20 times the log, and then they'll take the magnitude of simply eta naught over 4 eta shield here, plus 20 times the log of the magnitude of e to the d over the skin depth. All right. They'll call this loss due to reflection. It really has to do with the impedance discontinuities. They'll talk about this as loss due to attenuation, because that's where the signal is actually shorted out inside the material. Follow me on that, class? That's the only thing you have to really concern yourself with shield is know the terminology and know how to do the analysis. If for whatever reason you're given a problem where it's not a true shield, there just happens to be some barrier between things, and you have to do an analysis of how much field gets on the other side, I want you to understand what I've done here is the standard method that you get, but this is the worst case scenario. All right, now you get a field inside here, and it comes and it hits, then some of it's transmitted, some of it's reflected. Comes back, hits here. Does everybody follow me on this? Some of it's transmitted this way, some of it's reflected, and you get this bouncing inside and out. Now that problem, they do two ways. They track literally that thing in the time domain. But if you have to do an analysis of something that's got some wacky kind of, I mean, it's just too thin to assume that you get no reflections, then the way you do it is this. And I want to put this down for you. Wentworth puts it in his book too, and this is important. You actually see this once. So you remember how you did transmission line problems, right? Back in the day? Well, you do shield problems that way too. Then what you can do is this. You can say our problem, our shield right here, of thickness D, all right? We have some incident field here coming in. We have eta shield here. And then we have a transmitted field here. What Wentworth does is say, and he does a pretty good job about this, he says that how we can view this, and he does an analogy on this one. In his book, I have to check one thing. Yeah, this is going to be the LOSSY equation, and I'll talk about that in a second. This is on page 527, and he does put this point right here at z equals 0. And he's assuming this is the positive z-axis, and then therefore this would be z equals minus d. And he draws a parallel problem to this. He says these are exact parallels in every way, an exact analogy. He says instead of having an electric field that's propagating in free space, you actually have a voltage waveform that's propagating in a constant impedance Z0. So he says the way we can view this is have some impedance Z0 here, all right, and have a wave of voltage, and he's going to call this right here plus to minus V0 right here. And V0 is the same thing as E incident. I'll call it V0. All right, now here on the shield, what happens is now he's going to have a transmission line, and it's going to be a lossy transmission line. Just listen to me here and you'll understand. This is going to have a characteristic impedance Z0 of the shield, and it's got a certain length D, right? And then it's got a load, but the load is going to be assumed to be just the characteristic impedance of free space. Z0 is eta naught. Z0 over here is eta naught. And as a matter of fact, he shows this, yeah, he's got that, like this. Now, just follow me on this. This represents all the free space on that side. It goes on forever, so we just put a load there, which is Z0. Here's the actual transmission line, but this is a lossy transmission line, so the characteristic impedance here is lossy. I'm going to put the equation for it. I don't expect you to remember this one, but I want you to see it. So when we have this problem, really, the way I'm going to draw it is this. So you'll see it as a real transmission line problem. What this looks like is we have a load here at 0, and it should be at 0, but this should actually be at z equals 0 right here. We have a load that is just eta naught. That's what it looks like. Now, eta naught shield, that's going to be equal to the characteristic, when I talk about eta naught of the shield, it's going to be at the characteristic impedance of the shield, which is eta SH. Remember, that's going to be complex, right? That's like Z naught from before. Then it's going to be multiplied by the load, which is eta naught, plus, and not a J here, you just put eta shield, but then it's the hyperbolic tangent of, and now you've got to literally put in gamma. Gamma has a real and imaginary part. That's gamma of the shield times the thickness d over eta of the shield plus, and then eta naught times tan of gamma of the shield times d. Right there. And that's actually, I call this Z, or call it eta n of the shield at point D. So this is what the input impedance of this looks like. Do you follow me on this, class? All right? I mean, you're wondering, am I going to be required to solve a problem like this on a test? Probably not, but maybe on homework and maybe on quiz. All right? So I want you to follow me on this one. That's complex. Eta naught's 120 pi. Gamma is gamma of the shield. The one thing you remember with gamma of the shield, it's 1 plus J times, it's over there. See that right there? It's just simply 1 plus J times 1 over the skin depth. See that? Can you all see that? So that's what gamma of the shield is, and that's the input on the shield. Now here, follow me on this, just so we can get through this one time. If you have a wave coming in here, the amount transmitted here to the other side is going to be equal to, do you remember how to do this? We have to find the input impedance here, right? I'm going to remember this, that we have to find the input impedance of the shield, and what we do is make it look like this. Now we're going to have this V naught right here is actually equal to E naught incident, and it parallels that. Then you're going to have a characteristic impedance here of just Z naught, right? I mean, that's going to be in series. And then you're going to have eta of the, really the input of the shield, eta n here of the shield at a distance d. And you're going to find this value of voltage. You're going to have plus to minus, and I'll call it V prime. Follow me on this? That's just like when we did this transmission line problems with the lossless case. Do y'all remember this? Now that V prime is equal to what? Well, V prime there would be equal to some V naught on the transmission line plus, and then it's times e to the what? Minus, and now it's going to be gamma d plus the reflection coefficient at the load times e to the plus gamma d. I'm going to tell you something. In Whitworth's book, he goes through a problem with this, but he doesn't detail the steps the way I'm trying to do them now at that level. Now, listen to me now. You remember before it was just e to the minus j beta times the length of the line plus gamma L times, and it actually, because this is going to be Z, this would be negative, this becomes positive and that becomes negative. I think you remember that, right? Now, here's the thing. Gamma L here is the reflection coefficient right here. Well, gamma L is equal to eta naught minus eta of the shield over eta naught plus eta of the shield. All right? That's the reflection coefficient that goes right there. Now the game is this. Right here you got the input of the shield, input impedance. Then you do voltage division from this source to get this. Got me on this, class? Now once I have this point, I set that equal to this and I solve for V naught plus, just like before. Do you all remember that? Once you solve for V naught plus, which is just 1 over this stuff, you can put V naught plus is equal to V prime over e to the gamma d plus reflection coefficient e to the minus gamma d. Once you solve for that, then you can find the actual voltage at the load, you could say, which is really it's equivalent to the transmitted electric field. This is how much of the electric field would be transmitted. It's the same thing as the transmitted field. And in fact, that would be equal to just this V0 plus whatever it is times 1 plus the reflection coefficient of the load. Do you all remember that one? How many do right here? Remember that? All right, now the thing is that gamma L is complex, and you don't take a magnitude of it. It's 1 plus gamma L times V0 will be the transmitted field. That's how you do a shield problem in the frequency domain. If it's thin and there's a possibility of a lot of bouncing, that'll get you the right answer. I don't recommend, if you ever make a shield, hopefully you never have to analyze it that way. That's the pain, and frankly, it's unnecessary. Just make the shield thicker, unless there's some ridiculous reason why you can't. So Whitworth does this in his book. How many have their books here? A couple of you. If you look on page 527, he goes through the problem with that in mind. Normally, all the shielding problems that you run into and that I'll give you will be either design or analyze a shield where the shield is acting like a shield, and you pretty much all those assumptions I gave you are correct. That's basic planar shields. Now, if I have time, this is sort of secondary topics. I'll get into the actual sleeve shields, like why coax cable shielding works, and then into things like how come twisted pair works so well for losses or to get rid of really interference from outside sources. If we have time, we'll get into that. But right now, the next thing I have to do is filters. What I've shown you, work a problem with this stuff, all right? I'm going to give you several problems for sure this time, and I'll make absolutely sure they post. What's odd is it's on one laptop, on OneNote. But why syncing doesn't occur beats me. I have to look on a second laptop to make sure it shows up. All right, now these are filters. Dr. Wentworth's book on filters is very down to earth. It's very simple. I've got to tell you one thing about filters. You cannot live without them. Most analog filters that I'm going to show you are very simple, but in the real world that we live in, almost all signal processing that's worth anything is done in the digital domain. It means there's digital filters. And my wife's working for Archangel. The guy who owns that used to be a professor here in this department. His name is Mike Green. They use microcontrollers, and they literally have packages for FIR filters, finite impulse response filters, for band pass, low pass, high pass, whatever you want. And they just put in the coefficients to get what they want. That's how it's done in the real world, because almost everything's sampled, and it's analyzed digitally, and it's analyzed in a very high-speed way. These are analog filters. The thing about an analog filter, it's dirt cheap. So remember that. It's dirt cheap to do these, and they work for most applications that are fairly low frequency, not high frequency. So first we talk about two types of filters. The first one is low pass. Most of you are familiar with that. Low pass means the lower frequencies are going to get through the filter and the higher frequencies are going to stop. So the standard way to do this, you look on the source side here, and a low pass filter, if you want a low pass, you can do it this way. You can put a resistor here, or the resistor is the last thing you think about. And then, well, low pass, I can put a capacitor here, and if I take my output here and my input here, I can prove to you, but I want to just talk this through first. You all see that that capacitor looks like an open circuit at DC, right? So whatever signal here is going to get through here, right? Because this is an open circuit, right? No current would flow at DC. Do you all see that, right? Now, if you look at this, as frequency starts going up, this becomes a short, right? So if I get the transfer function for this, I'll call it, let me do it in the S domain, H of S. This has an impedance of 1 over CS. Well, the actual response, V out over Vn, is simply equal to 1 over CS over R plus 1 over CS. Now here I've just took this impedance over the series combination of those two. It's voltage division. Does everybody see this? Please make sure you do. And then I can say that if I multiply top and bottom by CS, I get 1 over 1 plus S times RC. S is really equal to J omega. You forget the sigma value. And if you look at that, you start at S equals 0. The transfer function is 1. You can see definitely low frequencies pass. There comes a point when the magnitude of this is equal to 1, or omega is 1 over RC, or F is 1 over 2 pi RC. And now, all of a sudden, the magnitude of this added together is square root of 2, and it starts going down. It passes low frequencies. Follow me? That's the simplest low-pass filter. And it's a common one to see, by the way. Another low-pass filter you could do, I want to say one other thing. This filter, if you just put an output-input signal, it has one interesting thing, that at DC, if this is a high impedance load, virtually no current flows. Right? If this is touching a high impedance, like 2 megohms or higher, something like that. Another way to do a low pass is this. You could put an inductor, L, and you could put a resistor here, R. And this would be V out. And this would be V in. And I think everybody can see that V out over V in for this case would be equal to just R over R plus SL. And if you wanted to get the same form as this one, you can divide by R, so you have 1 over 1 plus S L over R. You'll notice they have the same form. Instead of RC, you have L over R in that case. Does everybody agree this is a low-pass filter? Signal on this side. You all see it? All right, let me just draw a source here. Well, the output here is going to fall off after you get past the frequency omega is equal to L over R, or F is equal to 1 over 2 pi L over R. Follow me on that, class? It's straightforward. That's low pass. High pass, you do the inverse on this. For high pass, well, what do I do if I tell you on a test, I want you to make a high pass filter with a certain break frequency, and I want you to use capacitors and resistors? What do? Well, you'd put the capacitor in series because I know it's short-sided high frequencies, right? And then I put the resistor here to ground. There would be my plus to minus V out. This is my plus to minus V in. The impedance of this is 1 over CS, and that's R. And you could calculate that yourself. Do you all agree with that? Without going into detail, you've had filters. These are cheap and they work. That's the reason I'm talking about them. They're dirt cheap, and they work for most things where you don't need a lot of roll-off. These are all 20 dB per decade roll-off, nothing higher than that. Another filter you could do is what? If I asked you to do a high-pass filter, this is input, that's output, with an inductor and a resistor, what would it look like? High pass. Well, now it would do what? It would look like resistor here, right, and inductor here, because the inductor's impedance is SL, isn't it? So that impedance goes to infinity at high frequencies. And in fact, these two filters have the same characteristics as far as their output impedance is concerned. I've got to tell you a difference, though. And Wentworth does talk about this in his book. When I look at this one at DC, what's the impedance of this one at DC? Just look. It's infinite. Look, that capacitor is an open circuit, isn't it, class? On this side at DC, it's infinite. What about this one at DC? What's the impedance of a capacitor at DC? 0, right? Right? Because the frequency is 0, there is no. So it looks like R. Follow me? This is low impedance input. This is high impedance input for low frequencies. You have to keep these things in mind sometimes. All right? Now, at high frequencies, though, what happens? At high frequencies, this looks like R, doesn't it? The input impedance, what about this one at high frequencies? It's infinite, right? Because this goes to infinity at high frequencies, right? Now, the truth is there's more to this because there's loads attached, but I didn't have time to get into that. And right now I'm about out of time, too. I got to give you a quiz. So, yeah. You want the quiz on Monday or you want it now? You just tell me. How many want it today? No, we'll do it today. We'll do it today. I said I'd do it today, and these kids want it. If it was unanimous, I'd change it, but it's not. So just put everything away. Everything away. No complaining. If you complain, I'll flunk all of you.